Okay, we now want to look at the parallel RLC response, and to do this we're going to consider just the non-excited version. It's a small step to go to the excited version, but we'll leave out any sources, and we'll just talk about an R, an L, and a C. Alright, so we have these three elements that are in parallel rather than in series, so they share a common voltage. Previously in the series RLC they shared a common current, IL. So we will write the equation of motion, and we're going to use KCL. That makes good sense because we have this one node up here. No point in going around two loops. So KCL, we have current leaving through the cap is IC, plus current leaving through the inductor is IL, plus current leaving through the resistor is IR, which is just VC over R. We'll write for the capacitor C, dVC dt, plus IL. Now I need to figure out what we're going to write for that. I'll leave that blank for a moment. We know that IL is equal to 1 over L, the integral of the voltage across the inductor from time 0 to time t, plus some initial current. All right, that's just a restatement of VL is equal to L dIL dt. All right, that's the integral form of it. So we need to plug that in up here. Didn't leave myself enough room here. 1 over L integral of VC dt plus I naught. This goes from 0 to t. Now I'm going to take the derivative. This is an integral differential equation because there's an integral and a derivative. I want to make this into a derivative only equation. So we'll take the derivative of both sides. Alright, so we'll do d dt of c dvc dt plus 1 over L integral from 0 to t of vc plus IO plus VC of t over R is equal to that. Alright? So when we take the derivative, we'll get C second derivative for the capacitor voltage plus 1 over L, and this will just become VC, plus the derivative of I naught, constant, is 0, plus 1 over R VC dot is equal to 0. Let's multiply through by, or divide through, what do I want to do? Let's divide through by C. Okay, so we'll divide through by C, and we'll get V double dot plus 1 over RC VC dot plus 1 over LC is equal to 0. And that is our differential equation. Now it happens to be a homogeneous differential equation because we didn't put a source in here. But by now we should appreciate the fact that we can solve these things separately. We can do the homogeneous or the transient response, natural response first, and then consider the particular later. And with constant valued excitation, the particular response is pretty trivial at this point. So to expedite this solution, we're going to leverage our standard form. So consider our standard form. Our standard, I'm not writing very well. Standard differential equation form. Okay, we have s squared plus, one of the forms was s squared plus 2 alpha s plus omega n squared. That was the characteristic equation. Characteristic. Let me write the differential equation here. It was VC double dot plus 2 alpha VC dot plus omega n squared VC is equal to 0. Okay? Now, what we want to do is line this up with our differential equation that we just solved, or we just derived. I'm sorry, up here I forgot my VC. Alright, and now we can associate some coefficients here. Right? This comes straight out as before. Omega n is equal to 1 over square root of LC. But here we're going to find a different alpha. Alpha in this case is going to be 1 over 2 RC. This is for the parallel RLC. Notice that to arrive at this, I didn't even have to solve the differential equation. I didn't even write the characteristic equation. Oh, I did by accident, but I didn't even need to. And right at this point, I can write the solution. I know that the solution is going to be of the form Vc of t is going to be some initial voltage cosine omega dt plus b sine omega dt times e to the minus alpha t. All right, it'll either be that form, okay, if underdamped, right, or it will be something like c e to the minus alpha 1t plus d e to the minus alpha 2t if overdamped, right, where omega d is, just like before, going to be defined as omega n squared minus alpha squared. But alpha here will be equal to 1 over 2 RC rather than R over 2L, right? And omega n is equal to 1 over square root of LC. And we'd written before alpha 1 was equal to alpha minus square root of alpha squared minus omega n squared, and alpha 2 was equal to alpha plus all of this good stuff, right? So right away I can just write the solution. We can leverage off of everything else that we've derived previously. Now, as a concluding statement, let me just write in summary. Okay, in summary, let's consider the damping factor, for the series RLC and for the parallel RLC. For the series RLC, we found that it was R over 2L. For the parallel case, we found that it was 1 over 2 RC. And we'll write the Q for a series RLC. We found that to have been, I'm going to write in terms of the characteristic impedance in this case, Z naught over R. And although I haven't shown it here, it's a small step to derive this, but for the parallel RLC, Q turns out to be R over Z naught, exactly opposite. And to understand that, just think about these two circuits. All right, when I have the first case in series and the second case in parallel. Now, in the first case where I have series, what's in common is I, right? And to extinguish the interchange of energy, going oscillation, I need to impede the current, leads to dissipation. I don't know if that's the best way to put it, but so therefore large resistance, large R, impedes I, okay, large R. And that's what we see in the first case for the series RLC. A large R gives you a low Q, meaning there's not going to be much oscillation. In a parallel circuit, impeding voltage leads to dissipation. Okay, I'm out of room. Dissipation. Okay, so how do we do that? If we put a large conductivity, basically bleeds off that voltage or discharges that voltage that is stored in the capacitor. And so in that case, if we put a small resistance, large conductivity, a small resistance in parallel with L and C, we will extinguish the oscillation. Think of it this way: if you wanted to do the opposite, if you wanted to sustain the oscillation forever, on the series circuit you would set the resistance to 0. Whereas in the parallel circuit, setting the resistance to 0 would short the L and C out and you'd have no oscillation. So in the parallel RLC, if you set the resistance to infinity, then the oscillation is sustained forever, and that's reflected by the quality factor expression R over Z0 for the parallel RLC.